Hello students, my name is Rohit Sahu. I am working as assistant professor in mechanical engineering department, GL Bajaj Institute of Technology and Management, Greater Noida. The content which I described during my lecture are introduction, in which I describe where we use ultrasonic techniques. The second was the nature of sound. The third is generation of ultrasound. So, so let me start the introduction of ultrasonic technique. So ultrasonic technique are widely used for the detection of internal defects in materials, but they can also be used for the detection of small surface cracks. Ultrasonic are used for the quality control inspection of part proceed materials such as rolled slabs, as well as for the inspection of finished components. The technique are also in regular use for in-service testing of part and assemblies. Sound is propagated through solid in several ways, and the nature of sound will be considered first. In solid medium, the sound waves propagate in different ways. What is sound waves? Sound waves are elastic wave which can be transmitted through fluid and the solid medium. The audible range of frequency is from about 20 Hz to about 20 kHz, but it is possible to produce elastic waves of the same nature as sound at frequencies up to 500 MHz. So elastic waves with frequency higher than the audible range are described as ultrasonic. The waves used for the non-destructive inspection or testing of material are usually within the frequency range of 0.5 MHz to 20 GHz. So we are using 0.5 MHz to 20 MHz whenever we are using a ultrasonic inspection or technique. So we talk about the nature of sound. In fluids, sound waves are of the longitudinal compression type in which particle displacement is in the direction of wave propagation. But in case of solid, that is different. In case of solid, they are shear waves with particle displacement normal to the direction of wave travel, and elastic surface waves can also occur. These later are termed as Rayleigh waves. In previous slide, we see the different type of wave are generated or propagate in a solid medium or maybe in a fluid. Okay, so in that particular slide, if you see that there are a different value of velocity corresponding to their medium in case of longitudinal sound waves are given at a particular conditions at atmospheric pressure and 15 degrees centigrade temperature. So when we talk about the shear waves, the velocity of the shear waves, how we find out that the velocity of the shear waves? Theoretically, the velocity of shear waves, Vs, denoted by Vs, within a solid is roughly half the longitudinal wave velocity. The velocity of the Rayleigh waves, so the Rayleigh waves are denoted by the Vr. So the velocity of the Rayleigh waves in a solid is about 90% of that of a shear waves. Wavelength. The wavelength is denoted by the lambda and is related to the frequency and the wave velocity. Yes. So V equal to lambda f. So where f is the frequency. And table 2 gives the wavelength of sound in various material and several frequency. In common with other type of waves, sound waves will only be reflected effectively by objectives which have dimensions equal to or greater than the wavelength of the radiation. It will seen from the table number 2 in the next slide that an ultrasonic beam with a frequency of 10 MHz will be capable of detecting defects in steel of size greater than 0.58 mm, but only defects larger than 4.65 mm would be observed if a frequency of 1.25 MHz were used. The wavelength of a different material as corresponding to frequency are shown in this table. If you see, there are a different level of frequency are given. And if we talk about the defects, for example, we take a steel. So in case of steel, when we want to find out the minor defects in a steel, then we required a high frequency wavelength. And the vice versa, when we required to find out the larger defects, we required a lesser frequency, low frequency. That, for example, 4.65 in case of steel, it's required 1.265 frequency. And for find out the minor defects in that particular steel, that 0.58 mm, so we require 10 megahertz frequency. Frequency play a very vital role to find out the defects in a component during testing through the ultrasonic technique. If we talk about high frequency sound, for example 5 megahertz for contact testing application would provide good sensitivity, which is a term referring to an ability to detect small material imperfections called discontinuity. This same sound frequency would also have good resolution, which is a term used to describe the ability of a testing system to display closely spaced discontinuity separately on the instrument screen. Some components, such as casting, can have a very large grain structure and, as a consequence, are difficult, if not impossible, to test with high frequency. The sound at a 5 megahertz cannot penetrate through the coarse grain material due to a scattering effect called attenuation or loss of ultrasonic energy. So, to test this coarse grain material, low frequency sound such as 1 megahertz would be selected. Sound at 1 megahertz would have good penetration but poor sensitivity and resolution. So as mentioned above, the objective of many NDT application is to look for the presence of discontinuity. A discontinuity can be many different conditions. Maybe cracks, slacks, porosity and stringers are the names of just a few. It would be wrong to use ultrasonic inspection to locate, for example, a crack and then to refer to the crack as a defect. A discontinuity can only be called a defect if exceed specific acceptance standards. If we have, for example, if we have two cracks of the same length but in different components, one may be acceptable but the other may not. Therefore, only one crack can be called a defect. So, how can we use ultrasound to locate discontinuity? So, we will look at the specific equipment in more detail later. Okay. So, we have looked at the basic principle of ultrasonic method. Most important, we now must look in more depth at the nature of ultrasound, which is at the heart of the method. It is very important to know how ultrasound is generated. So for generating the ultrasound, we use transducer. A transducer is a device which converts electrical energy into a mechanical vibration and vice versa. Sound generation, the piezoelectric effect. We have looked at the nature of sound. Now we will consider how sound is produced by the crystals contained within a probe. The piezoelectric effect is utilized, which is a property of certain crystals to convert electrical energy into a mechanical energy and vice versa, as you seen in a figure below. Okay, so the probe are often called transducer because they convert one kind of energy into the another kind, that is electrical energy into the sound energy and sound energy into the electrical energy. Certain crystalline materials show the piezoelectric effect, namely the crystal will dilate or strain. If a voltage is applied across the crystal's faces, conversely, an electrical field will be created in such a crystal. If it is subjected to a mechanical strain, the voltage produced will be proportional to the amount of strain. How sound is produced with the help of piezoelectric material? That is most important. So there are different type of piezoelectric materials crystals that may be natural occurring, artificial occurring, and manufactured and grown in solutions. So nowadays we are using man-made ceramic materials, but previously we are using quartz because the property of man-made ceramics material are better in compared to quartz. So the better property in terms of sound generation and resolution. A typical ceramic material is barium titanate, lead metaniobate, and lead zirconate are widely used nowadays. So when an alternating voltage is applied across the thickness of disk of piezoelectric material, the disk will contract and expand as we shown in slide number 12. The principle of that particular, how that particular compressive waves are generating. So in doing so, a compressive wave normal to the disk in the surrounding medium is generated. When quartz is used, the disk is cut in a particular direction from a natural crystal. But in case of transducer disk made from ceramic material such as barium titanate are composed of many of small crystals fused together, the crystals being permanently polarized to vibrate in one plane. When the transducer crystal vibrates at its natural frequency, wave generation is most efficient. This is determined by the dimension and the elastic constant of the material used. Hence, a 10 MHz crystal will be thinner than a 5 MHz crystal. A transducer for sound generation will also detect sound. An ultrasonic wave incident on a crystal will cause it to vibrate, producing an alternating current across the crystal faces. In some ultrasonic testing technique, two transducers are used, one to transmit the beam and the other acting as the receiver. But in very many cases, only one transducer is necessary. This acts as both transmitter and receiver. So ultrasound is transmitted as a series of pulses of extremely short duration, and during the time interval between the transmissions, the crystal can detect reflect signals. For any query, please write me at rohitsahu87@gmail.com. rohitsahu87@gmail.com. Thank you. To be continuing in the next session. Stay safe, stay home. Take care.